Okay, the next topic we're going to cover is probability, which we will cover this and next session. This first session, we're going to kind of get into the basics surrounding probability, the definitions, the different types of events, the rules, and then we're going to end with conditional probabilities and Bayes' theorem. Okay, the problem that I want you to think about throughout this lecture is this drug testing problem here. So the probability that a person at a certain company uses drugs is 3%. The probability of a true positive is 99%. The probability of a false positive is 2%. So given that we select a single person and they're diagnosed as being a drug user, we want to know what's the probability that it was a false positive. Okay, it may seem like an obvious, easy answer of 2%. It's not. So stay tuned and you'll understand why. Okay, so first off, a probability, it's a measure of the likelihood that something will happen. Okay, there are different ways to express probabilities. The three that most of us see the most are fractions, decimals, or percentages. Of those, you probably see percentages the most in mass media, whether you're reading something online or a paper or hearing a newscast on TV. Whatever it is, you often hear them expressed as percentages. Okay, there are a lot of definitions having to do with probability. I wouldn't waste too much time learning these. You don't have to memorize them, just understand them and how they all fit together. Okay, so just really quickly, an experiment is, as I say here, the performance of an act that could be repeated under identical conditions. Okay, an experiment is anything that you do where you're going to get a probability from it. Okay, the outcome is actually the result of the experiment. Okay, if you collect one or more outcomes, that could be an event. A simple event is one that absolutely cannot be broken down any further. Okay, so if you look at an event, that could be drawing a heart from a deck of cards. A simple event would be drawing an ace of hearts from the deck of cards, okay, because that cannot be broken down any further. There's only one ace of hearts per deck. Okay, if you take all the possible simple events from an experiment, that's known as the sample space. Okay, so you have 52 different simple events in a deck of cards. That is your sample space. And the probability of an event, kind of expanding on the definition from the previous slide, is a measure. It's a numerical expression of that event occurring. Okay, the odds are a different way of expressing a probability. It is, in its most basic terms, it's the chance of an event occurring divided by the chance of the event not occurring. Okay, so if you're looking at drawing, in this example here, a king from a regular deck of cards with no jokers in it, you have 4 kings, 48 other cards, so the odds are 4 to 48 or 1 to 12. Okay, you can often hear this expressed as 12 to 1 against getting a king. Okay, random sample, it's just basically a sample where you have every member having the same probability of being selected. Okay, it's basically a fair deck of cards, a fair coin, anything where all the probabilities have the same chance of hitting. Okay, a complement of an event is the opposite of an event. So if you have a 4 out of 52 chance of getting something, the complement of that would be 48 out of 52. So it's always 1 minus the probability gives you the complement. Mutually exclusive, these are events that cannot possibly happen at the same time. You cannot have a head and a tail at the same time. You cannot have a 2 and a 5 at the same time. You cannot draw a king and a queen at the same time. Okay, anything that cannot happen together Okay, if you look at all of the possible outcomes of an experiment, that's known as being collectively exhaustive. Conditional probabilities, okay, these are when the probability of one event is dependent in some way on the probability of the other event. It's a measure of that. And joint probability is, as would make sense from the definition, the simultaneous occurrence of two events. That would be a joint probability. Okay, so enough with the definitions. Let's get to some actual numbers here. Okay, all probabilities have to be between 0 and 1. Okay, 1 means it occurs every time. 0 means it never occurs. You cannot have a negative probability. You cannot have a probability of more than 1, because that means basically you have a greater than 100% chance of something happening, which sadly is not possible. Okay, and if you take all the probabilities together, okay, which was the collectively exhaustive set of events here, the sum of all of them together, adding them up, has to be 1. Okay. Okay, so we have the rules of probability. More specifically, if two events, A and B, are mutually exclusive, then the probability of either of them happening is the probability of the first event plus the probability of the second event. Okay, so if you had, in this example here, the probability of a king or a 10, that would be 1 out of 13 plus 1 out of 13. So that would be 2 out of 13 with the probability of a king or a 10. You have to add up the probabilities. Okay, as I mentioned earlier, a complement of an event is 1 minus the probability of the event occurring. Okay, and the general rule of addition, if the outcomes of an experiment are not mutually exclusive, then some events can overlap. They can have joint probabilities. Okay, this is the example, and I do apologize for all of the gambling related examples. To me, it's just the simplest way to think of probabilities. But if you have the probability of getting a 10 or a heart, you have to add the probability of getting a 10 to the probability of getting a heart, and then you have to subtract out the probability of both of them happening. Okay, so you're basically simplifying it to account for the probability that things happen together. Okay, and you won't always have this. This only happens if there's an overlap. In other words, if they're not mutually exclusive. Okay, you have rules of multiplication, and it's super important. One of the most common places to make mistakes with probabilities is you don't first look to see if the events are independent. Okay, there's a different way of handling things that are independent versus things that are dependent. Okay, so two events are independent, and just in general, but specifically the probabilities as well, if the occurrence of one does not alter the chance that the other will happen. Okay, so the probability of A given B is exactly the same as the probability of A happening on its own, or the probability of B given A is the same thing as the probability of B happening on its own. Okay, so for two independent events, the probability that A and B will occur is found by multiplying the probabilities. So the probability of two different events happening is the probability of the first happening times the probability of the second happening. Okay, so an example of independent events would be tossing a coin and drawing a card. One has absolutely nothing to do with the other. The probability of a coin coming up heads, given that you drew a 10, is the same thing as the probability of a coin coming up heads. The probability of drawing a 10, given that your coin came up heads, is the same thing as the probability of drawing a 10. Okay, one does not affect the other in any way. So the probability of two independent events occurring is just the product of the probabilities of the events occurring on their own. And this can be expanded to any number. As long as these events are independent, you can go on forever with this. Okay, so the probability of A and B and C and ... is the probability of each event occurring on its own multiplied by the probability of the other events occurring on their own. Okay, and you combine these guys to get what's known as the product rule. Okay, and you could see where that comes from. Okay, if you take, whoops. Okay, if you take this equation here, the probability of A given B, or the probability of B given A, and you substitute it in to this equation here, what you get is the probability of both A and B happening is going to be the probability of B times the probability of A given B, or the probability of A and B is going to be the probability of A times the probability of B given A. Okay, and this will be important down the road for when we talk about Bayes' theorem. Okay, and now, okay, the previous discussion was of independent events. Okay, now we're looking at dependent events. Okay, the probability, if two events are dependent, then the probability that event A occurs given that event B has already occurred, it's the probability of both of them occurring divided by the probability of B occurring. Okay, so this is all very abstract, so let's look at an actual example here. I think it makes things a lot simpler if you look at an example. So we have 20 cans of corn in a carton. We know that 5 of the 20 are defective. So the probability of selecting a defective can obviously is 5 out of 20. And the probability of a good one is its complement, 1 minus 5 out of 20, which is 15 out of 20. So what if we already selected a can and did not return it to the carton? Okay, then we have a conditional probability. Okay, because we've already altered the set of possible outcomes. So we have two possibilities. Either the first can was defective or the first can was not defective. And if the first can was defective, then we have now a 4 of 19 chance. If the first can was not defective, then we have a 5 of 19 chance. Okay, and this is probably not seeming like anything too complicated, but what happens when things do get a little more complicated? What happens when we have more and more possible events? Okay, so let's look at the general case of what we just discussed. And this is called Bayes' theorem, which is, as you'll see, extremely important to probabilities. Okay, so we're going to combine some ideas here. The fact that the probability of A and B occurring is the probability of A times the probability of B given A, and the probability of A given B is the probability of A and B divided by the probability of B occurring. What we can say, combining all of these ideas, the probability of A given B is equal to the probability of A times the probability of B given A divided by the probability of A times the probability of B given A plus the probability of A not occurring times the probability of B given A not occurring. Okay, so what we're doing here is we're accounting for both true and false positives in the denominator. That's where that extra stuff comes from. Okay, so let's look back at our example here. And I think this will make more sense once we put some actual numbers into it. Okay, so let's break down the information we have. Okay, and we could just assign it either way, but for in this case, let's say that event A is that they don't use, result A is that they don't use, and result B is that they have a positive result. Okay, so what we know, the probability of a positive result given that they don't use is 0.02. The probability that they don't use is 97% because we know the probability they do use is 3%. And again, we could have chosen any way to define it. We just have to be consistent with how you do it. So the probability of getting a positive result given that a person uses, we're told, is 99%. Okay, so when we plug all of this stuff into Bayes' theorem, okay, we're getting the probability that they don't use, given they got a positive result, is this combination here, and the probability that they don't use, given a positive result, is actually around 40%, okay, which may be very surprising. Okay, so take a moment to just absorb that, kind of how we got there, given where we started from. Okay, it's not a 2%, it's actually 40%. It's how all these ideas combine. And why Bayes' theorem is so important, it's infinitely expandable. And as you're going to see in some of the examples we do here and down the road, that becomes really important because you have lots of possibilities. If we wanted to expand this specific example, what if we had 5 different companies that administer drug tests, and we wanted overall, we wanted to know the probability that someone being tested at any of the 5 companies who was or wasn't a user was getting a positive or negative, a false or true positive or negative. Okay, we have any number of possibilities, and Bayes' theorem expands to account for that. So in the most general sense, if we have I different events, the probability of all of these events, any of these events, given a certain constraint, is given here. Okay, so this can go on forever and ever and ever. Okay, next week we'll pick up with some different ideas of probability.